Hey everyone, and welcome. Today, we're diving into a Leetcode problem called Build Array from Permutation. It sounds a little fancy, but don't worry, we'll break it down step by step. It's actually quite a neat puzzle. Our goal is to understand what the problem asks, and then figure out a couple of ways to solve it. Ready? Let's go. Alright, so here's the main task. We're given a list of numbers, which the problem calls nums. This list is special. It's what's known as a zero-based permutation. All that means is, if the list has, say, 6 numbers, then those numbers will be exactly 0, 1, 2, 3, 4, and 5, all mixed up in some order, and each appearing only once. Our job is to create a new list. Let's call it ANS. That's the exact same length as the input nums list. Now, how do we decide what numbers go into our ANS list? Well, for each position, or index, I in our ANS list, the value we put there, ANS, is determined by a little formula, nums. It looks a bit like a double dip into the nums list, doesn't it? We take the number at nums, and then we use that number as a new index to look into nums again. Whatever we find there is our answer for ANS. We'll walk through an example to make this super clear. And just a heads up on the constraints. The list length can be up to 1000. Okay, let's make this concrete with example 1. Our input nums is the list, 0, 2, 1, 5, 3, 4. We need to build our ANS list. Let's start with the first spot. Index 0, for ANS. So ANS 0 will be nums 0. First, what's nums 0? Looking at our input, nums 0 is 0. Now we plug that back in. Nums 0 becomes nums 0, which is still 0. So ANS 0 is 0. Next, for ANS, nums 0. What's nums 0? It's 2. So we need nums 0. Looking at the input, nums 0 is 1. So ANS 0 is 1. How about ANS 0? That's nums 0. Nums 0 is 1, so we need nums 0. Looking at the input, nums 0 is 2, so ANS 2 is 2. See the pattern? For ANS 3, nums 0 is 5, so we look at nums 0, which is 4. So ANS 3 is 4, and so on, until we fill the whole ANS list. The final ANS list becomes 0, 1, 2, 4, 5, 3. Hopefully that makes a bit more sense now. So what's the most direct way to tackle this? Well, since the problem asks us to build a new array ANS, let's just do exactly that. First, we'll figure out how long our input nums list is. Let's say it has n items. Then, we create a brand new list, ANS, and make sure it also has n spots, maybe filled with zeros initially. After that, we just loop through each position, from index 0 up to n-1. For each position, I, we calculate nums, just like in the example, and store that result in ANS. Pretty straightforward, right? Alright, here's what that first approach looks like in Python code. Don't worry if it seems like a lot at once. We'll peek at the important bits. It's actually quite simple, following the idea we just talked about. So looking at the code, the first couple of lines are for setup. This line, n equals len nums, just gets the length of our input list nums and stores it in a variable n. So if nums has 6 items, n will be 6. Then, ans equals 0n creates our new list, called ANS. It makes sure ANS has the same number of spots as nums, and it fills them all with zeros to start. Nice and tidy. Next up is the main part, the loop. This for I in range n. Part means we're going to visit every spot in our list, one by one. The variable I will be our current index, starting from 0 and going up to n-1. Inside the loop we have that key line, ans equals nums. This is where the magic happens. For the current spot I in our ANS list, we first look at nums at spot I. Let's say the value there is x. Then, we use that x as a new index and look into nums again, at nums. Whatever value we find there, that's what gets stored in ANS. And we do this for every I. So how does this first approach perform? For time, we loop through the nums list once to fill up the ANS array. If the list has n elements, we do about n operations. So we say the time complexity is order n, or big O of n. This is pretty efficient. For space, we created a whole new list, ANS, that's the same size as nums. So if nums has n elements, ANS also uses space for n elements. This means the space complexity is also order n. We're using extra memory proportional to the input size. This is a perfectly good solution, especially if creating a new array is fine. Now, for a bit of a challenge, what if we wanted to solve this without using extra space for a new ANS array? Can we modify the original nums array directly to hold the results? This is what we call an solution. and it aims for order 1 or constant extra space. The tricky part is, if we change nums too early, we might mess up a later calculation that needed the original nums. So we need a clever way to store both the original value of nums and the new value nums I per p in that single num spot, at least temporarily. The main idea is to use arithmetic. We can combine two numbers into one if we have a large enough constant. Think of it like stored underscore value equals original underscore value underscore here, plus some underscore big underscore constant new underscore value underscore that underscore should underscore be underscore here. Later, we can get the original underscore value underscore here using a modulo operation, and the new underscore value underscore that underscore should underscore be underscore here using division. Interesting, huh? Let's dive a bit deeper into this encoding. First, we pick our big constant. A good choice is just the length of the nums array. Let's call this length q. Since all original numbers are less than q, this works perfectly. Now we go through the nums array, one spot at a time, say at index I. The number currently sitting at nums is its original value for that spot. Let's remember this as old underscore val underscore at underscore I. The ultimate answer for ans should be nums old underscore val underscore at underscore I. But if old underscore val underscore at underscore I is an index we've already processed, nums old underscore val underscore at underscore I might already be an encoded number. To get its true original value, we take nums old underscore val underscore at underscore I modulo q. This gives us the actual number we want to eventually be at ans. Let's call this new underscore val underscore for underscore I. Now the encoding step. We update nums to become old underscore val underscore at underscore I, plus new underscore val underscore for underscore IQ. After we do this for every single spot in nums, each spot will hold one of these combined encoded numbers. Then, in a second pass, to get our final answers, we go through nums again. For each spot I, we just calculate nums divided by q, using integer division. This will give us new underscore val underscore for underscore I, which is exactly what we want. And here's the Python code for this in-place approach. It looks a bit more involved because of the two passes, one for encoding and one for decoding. But it's following that same logic we just discussed. Let's break it down. Okay, let's look at the first loop, the encoding pass. First, q equals len nums sets up our special multiplier, q, which is just the length of the list. Then, we loop through each index I. Inside the loop, this line, val underscore, component underscore, for underscore, the ans, underscore I equals nums, %q is key. Nums on the right side, inside the square brackets nums, is the original value that was at index I. Let's call this x. So nums is the number located at index x. This number is what we want our final answer at index I to be. But nums might have already been encoded if x was an index we processed earlier in this loop. So, nums %q cleverly extracts the true original value from nums, stripping away any encoding. This is our val underscore component, underscore for underscore ans, underscore I. Then, nums equals nums plus val underscore component, underscore for underscore ans, underscore IQ does the encoding. The nums on the right is the original number that was at index I. We're adding val underscore component, underscore for underscore ans, underscore I, our target answer for this spot, multiplied by q. So nums now holds a combined value. Its original content is recoverable by nums, %q, and the desired answer component is recoverable by nums, _. After the first loop is finished, every number in nums is an encoded value. Now, we need to extract our final answers. That's what the second loop, the decoding pass, does. It's much simpler. We just loop through each index I again. This time, we set nums equals nums/q. The slash symbol means integer division. So if nums was, say, original plus answer q, then dividing by q and taking the integer part just gives us answer. And just like that, nums now holds the final correct value nums that we wanted, and we did it all in place. Finally, we return the modified nums list. So how does this clever in-place method perform? For time, we actually go through the list twice, once to encode all the values, and a second time to decode them. If the list has n items, the first pass is about n operations, and the second is also about n operations. So roughly 2 n operations in total. When we talk about big O notation, we ignore constant factors, like the time complexity is still order n. It's just as fast, time-wise, as the first approach. Now for space, this is where it shines. We didn't create any new arrays or large data structures. We just modified the input nums array directly and used a few simple variables like q and I. This means the extra space we used is constant, or order 1. That's super efficient in terms of memory. So to wrap things up, we tackled the build array from permutation problem. The core task was to set each ans to nums. We saw a simple, direct way to do this by creating a new array. This approach is easy to understand and works great, using order n time and order n space. Then, we explored a more advanced technique to do it without using significant extra memory. This involved a cool trick of encoding two pieces of information, the original number and the new target number, into a single slot using multiplication and addition. Then, a second pass decoded these to get the final answer. This clever method still takes order n time, but achieves order 1 space complexity. Both are valid ways to solve it, each with its own trade-offs. Hope that breakdown made sense and helped you understand the problem and the solutions a bit better. If it did, feel free to hit that like button, or maybe subscribe for more explanations like this. If you have any questions or other ways to solve it, drop a comment below. I'd love to hear it. And hey, if you're feeling extra generous and found this super helpful, there's always the Boba Fund. Every little bit helps keep the explanations flowing. Keep practicing, keep coding, and I'll catch you in the next one.